Hello. So in this set of notes, we want to talk about the derivative of inverse functions. But first, what I would like to talk about is the derivative of a composite function. So if we have f of g of x, and I know that they're both differentiable, which remember just means that their derivative exists everywhere. How would I take the derivative of that? It should be the derivative of the outside. And since f is the outside, it would be f prime. And then g still inside, times the derivative of the inside, which is just g prime. So that's it. Now I want to consider what happens when I have two inverse functions in general composed together. So let's think about two inverse functions that we are familiar with. Could be x and x squared. It could be e and ln of x. Any two of your favorite inverse functions. I want you to write those down. Mine happen to be e in the natural log. Go ahead and compose them together. I don't care what order. I'm just going to follow f of g of x like I have written down below, but it could be the other way around. So basically for mine, I'm doing f of ln of x, or really e to the ln of x. And think about what happens when you have e and ln composed together. They cancel because they are inverses. They are opposites of each other. And I am left with x. It should happen regardless of what two inverse functions you choose. If you choose x and x squared, the square and the square root cancel and you're left with x. If you choose the cubic root and x to the cube or to the third power, those should cancel out. If you have a more complicated one, regardless, you should just get x as your very final output. So basically, when you compose two inverse functions, you should get x as a result. So if I take the derivative of those two inverse functions, I'm really taking the derivative of x, which is 1. We okay so far? Do we have any questions? If you have any questions, make sure you write them down. All right, so what I want to do is put all of this information together. The very first thing that I got up here was just thinking about if I took the derivative of two composed functions in general. But if I'm thinking about those as being inverse functions, I'm really taking the derivative of x, which is 1. So ignore what I have over here for a second. If I just wanted to know the derivative of that inside function by itself, really, it would just be g prime of x equals 1 over the derivative of the outside. So the derivative of the inside function is equal to 1 over the derivative of the outside. I want you to box this. This is really important. This is our derivative of inverse functions formula. Or you can say inverse derivative formula. And I'm going to bring that back. Okay, so then for anyone who is a visual learner or is just interested in the math behind all of this, I'm going to show you just some like random graph here below and another way that this works more visually. Keep in mind that any way that we do this visually is not something that I would test you over or quiz you over. It's just additional information to make sure, or to like get you a little further. It's not required information, just a bonus, basically. Not a bonus problem, just a bonus. Okay, so I have f and g here. I'm told that they are, I'm not told that they're inverses of one another, but I do know that inverse functions are reflections over the line y equals x, which I do have here. And I also know that when that happens, the coordinates on one function are like flip-flopped in the inverse function, which I do have going on. So AB in my one graph on its inverse graph is BA and vice versa. So the next thing that I want to talk about is F and G, because I have this graph F right here and I have the red line touching it. Can you tell me what that is? Hopefully you said out loud to yourself that it looks like a tangent line and that it's a tangent line at what point specifically on F? A, the tangent line at A. And what do we know about the slope of this tangent line? Well, the slope of the tangent line is the derivative. And specifically, it's at A because it's touching A. So it's the derivative of F at A. So I want you to do the same thing over here for the g of x graph. We have a red line that is just grazing it as well. So what is the slope of that line equal to? Hopefully you said, I am so sorry, g prime of b. Make my prime a little bit more obvious. Okay, so let's actually calculate those slopes. Let's do f prime of a. So we're looking at the slope of this bottom red line. And I actually already have 2 points pointed out for us on that line, A, B, and C, D. And remember the slope is change in y. So I'm going to do the blue point minus the red point, B minus D, over the change in x, and that would be A minus C. Go ahead and do the same thing to figure out the slope of the line that touches G. Change in y's over there would be A minus C, since those are the y values, over B minus D. If you have this in the exact opposite order, that's perfectly okay. I would prefer in mind to have the right minus or the blue dot minus the red dot, just so that I can be consistent. But if you do the red dot minus the blue, that is okay. Oh, I'm sorry, that's not g prime of A. I made a typo. G prime of B. So what we just did is we figured out those derivatives from the actual visual itself. But let's pretend that I didn't know what the graph of g of x looked like, and all I knew was one piece of information about it. What's another way that I can figure out what g prime of b is? Well, I know that it's the inverse function of f, so technically I can use the inverse derivative formula. So I want you to go ahead and use that inverse derivative formula that I have at the top of the screen and fill that out, but use b as our input instead of x. Okay. So in order to figure out what this value is, I at least need to know one piece of information about g, which is, so I know that is A. I could use the graph to know that, or I know that f of A equals B, so it's inverse order would be that. Okay, so really I'm doing 1 over f prime of A. That looks terrible. So that's 1 over We already calculated f prime of a. That was b minus d over a minus c. And 1 over a fraction is its reciprocal. So technically that's a minus c over b minus d, which we had proven before. Okay, so like I said, this is just additional information if you wanted to see the visual mathematics behind it. Let's move on to some examples. Okay, so example 1 says, let g of x be the inverse of the function f of x equals x plus e to the x. Find g prime of 1. So first and foremost, I am going to, I'm actually not going to do that. I want to talk about why we're not going to find g of x in the first place. Can you remember how we find inverse functions? So the process is that we switch the x and the y around. So I'll put the x where technically, quote unquote, the y is, and I'll put y's where the x's are. Think about how difficult that would be to solve for y, because that's what we would do next. We would solve for y so that we could actually have a y equals function. That would be awful. I don't even know if that's really doable using any of the techniques that we know or any of the algebra that we know. So in order to figure out the derivative of g at 1, I'm going to use my inverse derivative formula. Want you to pause the video and write down what g prime of would be using that derivative formula. Here it is, derivative of the outside with g of 1 plugged in. So what information do I actually need to know in order to move forward with this? We definitely need to know what g of 1 is. And we'll need to figure out what the derivative of f is. But I know what f of x is, so I can figure out the derivative function just by doing that as side work. That would be 1 plus e to the x. So we'll use that later. Let's focus on figuring out what g of 1 is now. So I know that g of 1 is going to equal some number. But if I recognize that f of x is its inverse function, the relationship between g and f is that their inputs and outputs are flip-flopped. So this technically means that f of some number equals 1. I need to figure out what that number is. So what I'm thinking in my head is, well, what number makes f of x equal to 1? Now, you can go ahead and solve that equation. I don't want to. This is actually a pretty easy one to analytically think about, like guess and check, plug and chug. So I want you to pause the video and do a little bit of thinking about what that x value could be so that that output is 1. I know that it happens to be 0, just because if I have 0 in for either of the x's, technically I'm getting 0 plus e to the 0, which is 0 plus 1. So I know that the number I need is 0. So technically f of 0 equals 1, which means that g of 1 equals 0. So I can move forward. So I'm really finding f prime of 0. And since I already found my derivative function, I just need to plug it in. And that means that g prime of 1 equals 1 over 2. Alrighty, if you have questions, definitely write them down. That way you can ask me in class. For now, I would like you guys to all try So first and foremost, I need g of 2. So I know that g of 2 equals some number, then the opposite of true for its inverse function, f of some number equals 2. And if you read the problem, it tells us what that number is. F of 1 equals 2. So that means that g of 2 equals 1. And it also tells us what f prime 1 is. That is 1/3. 1/1/3 is 3. Okay. So if you're still having difficulty with using the inverse derivative formula, I can give you a whole bunch of problems on Delta Math. This is actually not a terribly difficult thing. It's just kind of following a formula and thinking analytically about what information do you need in the first place. Okay, so let's move on to inverse trigonometric functions. So remember what what a regular trig function takes in. If I do sine of theta, I'm technically putting an angle in, and what I get out is either a coordinate, if it's sine or cosine, or I'm getting a ratio of the coordinates. So then an inverse trig function, remember inverse functions in general, the inputs and outputs are flip-flopped. So technically an inverse trig function is going to take in a coordinate or a ratio, depending on which one it is. And it is going to output an angle. Okay. So in example 3, I am looking at some information to help us figure out what we need in example 4. Because example 4, it says find the derivative of sine inverse of x. The beginning of the notes was all about inverse derivative or inverse function derivatives. We have that formula. We can use that technically, but we need some additional information in order to do that with inverse trig functions. So what I would like to do first is go to example 4, and then we'll revisit this in a second. So in example 4, we're told to find sine inverse of x. Please remember and write down what the inverse derivative formula looks like. So remember, f and g are inverse functions. If I want to find g prime of x, in this case, it's my g of x that I'm going to use as sine inverse. And the outside function needs to be its inverse, which the inverse of sine inverse is just sine. So we'll go forward with that in a minute, but the information that we're going to need in order to go a little bit further with this, we need to fill out an example 3. It's going to feel a little disconnected, but that's okay. This is pretty much like I said before, the visual behind the math here. You don't need to memorize example 3. You don't need to memorize example 4. We're just building up our inverse trig derivatives. This is just something that I think some of you might appreciate. If you don't appreciate it, that's fine. Just memorize the trig table on the next page. So here it says, in order to do this, let's construct a right triangle in the unit circle for some angle theta, where theta equals sine inverse of x. Well, in this triangle, I want to label the sides. So what I'm going to do is solve for, well, not solve for, I want to figure out what sine of theta is. Because I know the ratios of a right triangle are like For sine, it's opposite over hypotenuse. So if I take sine of both sides, sine and sine inverse cancel, and I'm left with x equals sine of theta. Now, since sine of theta is opposite over hypotenuse, I'm going to put this over 1. And I'm going to label that in my triangle. So I have my theta labeled, opposite is x, and hypotenuse is 1. Let's figure out this missing side here. We have a right triangle, guys. How can you find the missing side on a right triangle? Hopefully I heard Pythagorean theorem. So we have a squared plus b squared, which is our other leg. So I'm just going to put x squared equals c squared. Or in our case, since the hypotenuse is 1, 1 squared. So trying to get a, which is our missing side by itself, we get a squared equals 1 minus x squared, or a equals the square root of 1 minus x squared. And we're just going to use the positive version of this measurement. Then we are, in the rest of the problem above, told to find cosine of theta. Cosine is adjacent over hypotenuse. And in this triangle, that would be square root of 1 minus x squared over 1, which is just the square root of 1 minus x squared. So if you don't want to write the over 1, you don't have to. So let's see why in the world we even needed all of this information by moving on to example 4. Okay. So we have some of this filled out. Let's go ahead and just write the 1 over the inverse derivative formula. 1 over g of x. I'm actually going to write sine inverse of x in there. And let's see. We already know what f of x is. What's the derivative? Cosine? And sine inverse of x is still in there. Now, in example 3, we were told that theta equals sine of inverse x. So I'm actually going to replace that in there. And that is exactly why we needed to figure out what cosine of theta was. We know what this is from example 3. Cosine of theta was the square root of 1 minus x squared. So might seem like I just pulled this out of my butt, but the derivative of sine inverse is actually 1 over the square root of 1 minus x squared. So if you want to do a similar process for any of the other trig derivatives, basically what you would do, I'll show you on the back, you would say, let theta equal that value, or that inverse trig function, solve for the x. So that would be, in this case, secant of theta equals secant of secant inverse, or x. And then use the trig ratios there. It doesn't need to be a unit circle. It shouldn't actually be labeled as one for me. But you would use your trig ratios to fill out the right triangle that you have drawn in there. And then you could figure out what you need your inside and outside function is to be, and what other information you might need from that triangle. Like in this case, we needed to also figure out cosine theta. So once you figure out the derivative of the outside, you might need to use that triangle to figure out that outside value of theta as well. If you are at all interested in that, stick around to the very end of the video and I will finish that one on the very last page. If you are not interested, let's just dive right into the derivative of all of the inverse trig functions. Cosine inverse, it's the same as sine inverse, but negative. Tangent inverse, that would be 1 over no square root and everything's positive. Cotangent, you might have guessed it, same as tangent inverse, but negative, just in the numerator. Or I guess you could make the, never mind. Secant, you'll find out later on the back of, well, you will find out later if you want to continue to the back, but we're going to need it for the next example anyway. It's 1 over the absolute value of x times the square root of x squared minus 1. So if this one's a little difficult to remember, at least remember that it has x before the root. So when you go into the root, it'll start with the x squared. And then I bet you guessed the last one. Same thing as secant inverse, but negative. Now, some examples will not have the absolute value, and that is perfectly fine. It's just if you go to evaluate this, you need to have those absolute value bars around that x. Okay. And I am going to skip what I have all that extra space for and just go into example 5. So example 5 says, compute the derivative of h of x equals arcsecant of e to the x plus 1. Guys, if you have never seen arcsecant, that is literally just another way to say secant inverse. So what kind of function do I have going on here? I know that I have an inverse function. So other than that, what else is going on? Hopefully you're recognizing that we have something plugged into secant inverse. So we technically have a composition. What's my inside? What's my outside? Inside is e to the x plus 1. Outside is secant inverse. Okay. So if you're the type of person that likes to write the derivative of the inside and the outside down, go ahead. Look back at the screen when you're ready to see what the derivative of the inside and outside is. You can use your table for the derivative of the outside. Okay. So h prime of x. That is the derivative of the outside. And I'm just going to actually put g in there instead, like e to the x plus 1 instead of that. Oops, that was supposed to be a 1. And you do not need to simplify this unless you are asked to do something further with it. Don't bother doing that. That's too much work. All right, so that's the derivative of the outside times the derivative of the inside, which if you wanted to simplify, at the very least, you could write e to the x in the numerator and just be done with it. And then who remembers how we could check our answers? You could put h of x in your calculator, and you could put your derivative in the calculator, have your calculator calculate its derivative and see if your answers match. Now, I'm also just going to show you Desmos really quick, because you can technically check your answers on Desmos. It's not like you're allowed to use Desmos on a quiz, so calm down here. But you could at least check your stuff whenever you don't have your calculator available. So I'm going to turn off h of x. That way I can just compare the derivatives that I have. All right, and those end up being the same exact graph. So yay. Or if you want to zoom out a lot, it just ends up looking like a line. That's why I don't want to do it. But yep, same graph. All right, so those of you who wanted to stick around to the end, continue on with the video. If you do not want to look at this, go ahead and log out. You are done with the notes. Okay. So if I wanted to figure out the derivative of this from here, I need to at the very least put the information in and find my missing side. So secant, that's the reciprocal of cosine. Cosine was adjacent over hypotenuse, so I know that this would be hypotenuse over adjacent. All right, so that would be x over adjacent, which would be 1. And then let's figure out our missing side. All right, so a squared, I'm going to use that as 1 squared, plus b squared is my other leg, equals c squared, which is my hypotenuse squared. Let's go ahead and solve for b squared. I'm just going to type this. And then b would be the square root of that. Again, I'm just going to type. Okay, so I will put that in there. It looks similar to what we did in example 3, except that was backwards. I think the missing side there was square root of 1 minus x squared because we had different information that was provided. So let's go ahead and start figuring out what the derivative would be. So if I want to know the derivative of secant inverse, since that's my inverse function, I'm going to say let that be g of x. And that's also the one that I want to know the derivative of. And f of x would be its inverse, which is just regular secant. G prime of x equals the inverse derivative formula. So 1 over f prime of g of x. And I'm actually going to fill in the g of x there. And let's take the derivative of f. F is secant. What's the derivative of secant? Secant tangent. Just keep in mind here that the input is actually secant inverse. So even though I have secant tangent, secant inverse goes inside of both of those. Okay. I know that secant and secant inverse, since they're inverses, they cancel, and I'm left with 1 over x there. But in order to figure this stuff out, you remember how in example 4 we had cosine of sine inverse? Well, that's where we had the right triangle and we were given in the first place that theta equals sine inverse. So here, remember how we have theta equals secant inverse? I am going to replace this with theta. So really, I have x times tangent x. Or, I'm sorry, x times tangent of theta. And maybe I will just write that. So I am going to go up above and do a little bit of side work to figure out what tangent of theta is. Do I have my Greek letters anywhere? Okay. So tangent is sine over cosine or opposite over adjacent. Opposite being square root of x squared minus 1. Over adjacent, which is just 1. So really tangent is just square root of x squared minus 1. And there you have it, folks. We just found out the derivative of secant inverse is x, or 1 over x times the square root of x minus 1. The only thing that we didn't derive here was that absolute value portion. I honestly forgot how that works, but if you're really, really interested, I can look further into that and remind myself of why that works that way. Otherwise, have a great whatever time of day it is for you, and I will see you in class.